Hi, this video will cover section 3.6 for the class Math 1324. And we're going to start here by looking at what is the definition of a rational function. So a rational function, it's going to be a ratio of two polynomials. And so we already know that this is a polynomial of second degree. This is a polynomial of third degree because I'm looking at the highest exponent. In this case, we have a polynomial of first degree, polynomial of first degree. Now, this number it also happens to be a polynomial. We could say it's a polynomial of degree 0, x to the power 0. Remember, x to the power 0 is equal to 1. And the degree here of the denominator is a 1. So what we do with these functions is we can refer to this as bottom heavy. The next one will be of the same degree. And this one is also bottom heavy. So I'm going to give you an example of how a top heavy function will look like. And so we could have something like, let's call it k of x. And we could say x cubed plus 1. And then on the bottom, I'm just going to have x minus 2. So in this case, the degree of the numerator is a 3 and the denominator is a 1. So we can refer to this as a top heavy function. Okay, so one of the conditions for this function to be a rational function is that the denominator is never equal to 0, because you already know that if that was to happen, then we will have an undefined function for that particular x value. So we're going to have to look for those x values that will cause the denominator to equal 0. And those numbers, those x values, are going to cause some breaks in the graph, and we will see those in the form of vertical asymptotes. So for example 1, we have a function 2 divided by 1 plus x. And so first, let's just use what we learned from last chapter about finding the domain of a function. In this case, we take the denominator, which is 1 plus x, and we create an inequality that tells us that cannot equal to 0. So if we solve for x, we will get x cannot equal to negative 1. And in reality, that is what we see here. Here, right in the middle, we will have the number negative 1. Or x equals negative 1. Now, what we see here on the right side are numbers that will be on the right side of negative 1. And they're very close to negative 1. However, they're not exactly negative 1. Now, what we see on this left side of negative 1 are numbers that will be on the left side of negative 1. And they are close to negative 1, but still on the left side. We could say they're smaller. And so we're going to say that for these numbers, we have the numbers are approaching x equals negative 1 from the right. And on this side, we have the x values are approaching x equals negative 1 from the left. Now we're going to write down what the function values will be for this particular x values. So for x equals negative 1.5, so we'll have negative 4. For x equals negative 1.2, we'll have negative 10. Then we will have negative 20. We'll have for negative 1 0.01, so that's even closer to x equals -1. And you could see that the value is going to decrease. And I say decrease because, yeah, we are getting numbers with bigger absolute value, but since they're negative, they're going down to -infinity. Now, right here, if we were to substitute -1 in this function, we will get an error on the calculator, but we know that means undefined. So now moving on, let's say I'm approaching my x equals -1 from the right. And for this x value, I'm going to get +4. For this x value, I will get not negative, but +10. For this x value, I'm going to get 20. And then it's going to go up to 200. So what we could say is that while the x values approach x equals -1 from the right, the y values are approaching +infinity. And we could see that on the graph. We're on the right side of x equals -1. The y values are going up to infinity. They're getting larger. On the other side, which will be on the left side of x equals -1, you could see how the y values are decreasing. They're getting more negative, therefore they're getting smaller. So we could say that the y values are approaching -infinity, or in other words, the function value is approaching -infinity. And we could see that graphically here, the y values are approaching -infinity. So, like we mentioned before, that same exclusion from your domain that will cause the denominator to equal 0 will also be your vertical asymptote right here. Now, there's another thing called the horizontal asymptote, and of course that one, we have 3 conditions. One is for bottom-heavy functions, one is for same degree, and one is for top-heavy. So if your function is bottom-heavy, by default, the horizontal asymptote, by the way, we use HA, we don't want to write the whole thing, it will be by default y equals 0, which is this line. When you graph this on MyMathLab, make sure that you do graph your lines dashed or dotted, because if you don't, then MyMathLab will count it wrong. Now let's see what happens with its x values starting from 0. So if x was 0, the y value will be a 2. What happens if we increase our x value? So we say x approaches infinity, and so the next y value for x equals 9, it will be 0.2. For x equals 99, it will be 0.02. And so you could see that what's happening, the y values are getting smaller. If we were to put a 999 here, the y value will be 0.002. And so they are getting smaller, but they're not going to become negative. In fact, they're just going to approach 0. Now, if we look on the left side of the y-axis, when x equals -2, the y value is also -2. When x equals -1, the y value is -0.2. And when x equals -101, the y value is -0.02. And so we could say here that as x approaches -infinity, meaning that the x values are getting smaller, the y value is going to approach as well 0. And those values are going to stay here, get close to the line y equals 0, which is the horizontal asymptote, but the graph will not cross that horizontal asymptote. Therefore, those values will still be negative. They will not become positive, and they will never be 0. Now, on this side, they will get smaller and smaller, approaching 0, but they will not become 0 or negative. So we're going to graph the next problem, and this is what summarizes what we said about that number that makes the denominator 0. the one that we have to exclude from our domain is going to be the same number that we use with our vertical asymptote. So in this case, we're going to work this by steps. So our first step is going to be to find the domain. And for that, we take the denominator 2x plus 4. We create an inequality that says that cannot equal 0. So therefore, 2x cannot equal negative 4, or x cannot equal negative 4 divided by 2, which we all know is going to give us negative 2. So that exclusion from the domain, if I had to enter the domain as an interval, I would say the domain will be all real numbers except for that. So negative infinity to negative 2, parentheses, because negative 2 is not included, then union, parentheses, negative 2 to positive infinity. That would be the domain. Now, our second step is going to be to find the vertical asymptote. And for that, it will be the same number that we excluded from the domain, which will be x equals 2. So let's go ahead and graph it here. And it needs to be a vertical line going across x equals negative 2. And I'm drawing a dash because it's not actually part of the function, is what the function cannot touch. So next step I'm going to do is find the horizontal asymptote. And with that, going back to the equation, we have the degree of the numerator is a 1, denominator is also a 1. And so we have same degree. And so by default, the horizontal asymptote is going to be the ratio of the two leading coefficients. So those will be the big numbers that are with the x to the power 1. So we will have a 3 and a 2. So that will be the ratio between 3 divided by 2. So in other words, the horizontal asymptote will be the line 3/2. And if you feel more comfortable, we could call it 1.5 as a decimal. And so we're going to graph this one, horizontal line. It goes there. And so now we need to figure out how our graph is going to behave. So it is useful to select, well, for example, we could find the y-intercept. If it's a y-intercept, it has to be a point on the y-axis, so therefore the x value is 0 by default. So to find the y value, we're going to use the same equation, the original equation here, but now we're going to make each x equal to 0. So 3 times 0 plus 2 divided by 2 times 0 plus 4. And so you can see here that will go to 0, so we're going to have 2 over 4, which is simplified into 1/2. So the y-intercept will be the point 0, 1/2, and that will be here on the y-axis. Now finally, to find the x-intercept, we already know we're going to let y equals 0, and we're going to solve for x. So if we take the original equation, but now we make that y equals 0, we have not 2, but 3x plus 2 divided by 2x plus 4. And so you all know that the denominator that is down here is dividing to the 3x plus 2. And so if we were to move that denominator, all of it together to the left side, we will have that multiplied by 0. And so that multiplied by 0 will just equal to 0. So now we have this equation, 0 equals 3x plus 2. So now to solve for x, and we will have that negative 2 is equal to 3x. So therefore, x will equal to negative 2 divided by 3. And negative 2/3, so that would be somewhere before negative 1. And so it would be here. Now I'm going to draw the graph. So I'm going to make sure to go across the y and the x-intercept, but I'm not going to touch the vertical and the horizontal asymptotes. So you see right here is going down to infinity. And then the other part of the rational function will be like that. Now, another useful way to get a better image of the graph is to graph it on your calculator and look at the table. You can get more points to get a more accurate representation of the graph. So we're going to go to the next slide, and here's just a summary of what we just went over. So whenever you have a rational function that top and bottom are of the same degree, what you do to find the horizontal asymptote is to find the ratio of the leading coefficients. In this case, we're using the letters A and C just to generalize that they're numbers. So right here we have, again, same degree. And so we're going to graph number one. We're going to start by identifying the domain, because that's going to help us to find our vertical asymptotes. So we take the denominator x squared minus 4, create an inequality that says that cannot equal to 0. And here we could solve it by factoring. This is a difference of squares, so it will be the product of x plus 2 and x minus 2. That cannot equal 0. From here, we could, by the zero factor property, we could take each factor and solve the inequality one at a time. So we'll get x cannot equal negative 2. And from the other factor, x minus 2 does not equal 0. Solving for x will give me x does not equal positive 2. So right there, those are the exclusions from the domain. So now to write them as vertical asymptotes, we will just use the same letter, x equals, so x equals 2 and x equals negative 2. So I'm going to go ahead and graph them here. Remember, they are vertical lines. So go there. And now we're going to go ahead with our step 2. Now let's go ahead and find step 3, which will be our horizontal asymptote. And we, again, have same degree, so we have to look at the leading coefficients. We have a 2 and a 1. So that's going to be the ratio of 2 over 1, or in other words, just 2. So that's going to be our horizontal asymptote, y equals 2. So it will be this horizontal line going across that value, y equals 2. Now we have a rough sketch of how the graph will look on the calculator. Graphing calculators do not give you vertical or horizontal asymptotes unless you have the updated version of a TI-84. Even then, they do not give you horizontal asymptotes. Some of them are giving the vertical ones. So we still need to figure out where this graph, or how is it going to look. So if you wouldn't have a graphing calculator handy, then the next step will be to find the, let's find the y-intercept or the x-intercept. Now, I already know what the x and y-intercept will be, and that's why I chose to find the y-intercept first, because I personally think it's easier. So now what I'm going to do is substitute every x with a 0. And I'm substituting from the original equation here. And so this will go to 0, and this will go to 0 minus 4, which is negative 4. And 0 divided by negative 4 is just 0. So the x-intercept happens to also be the y-intercept. Now, just to finish graphing this, what we did in class was we graphed it on our calculator. And it is very important that when you graph it on the calculator, you enclose the denominator in parentheses. You must do that or you will not get the correct graph. So what we did was we looked at the table after graphing it to see how the graph was going to behave. So we found the y values or the outputs for this x values that I'm writing down here, -3, -1, 1, and +3. Now, I chose those values because they happen to be on the left side of the asymptote or on the right side of the asymptote or in between the asymptotes. Like, for example, -1 and +1 for x, these are in between the asymptotes. And so we looked at the graph at the table, actually, for those. And they were the following: -0.667. And also for x equals +1, the answer was -0.667, which happens to be -2/3. So that point will be here and here. So that's how the graph will look, kind of like a parabola, oops, without touching the vertical asymptotes. Now for x equals -3, what did I get? I think it was like a 3.6. I'm trying to find those on it was around 3.6, so let's just do that. So 3 for x equals -3, 3.6, so a little bit past 3.5 for the y value. Now, if the x value is +3, the y value will be 3.6, somewhere there. And so the graph, just to finish, again, it looked like that. When you graph this on MyMathLab, make sure you do include the asymptotes and make sure you do make them dash or dotted, because if you don't, MyMathLab will count it wrong. And that's it for the graph of that one. Now, the next problem here, I'm going to just leave it there for you to read, but it is about cost-benefit functions. And the situation that we are showcasing here is how much it will cost based on percentage. So the x values, or your independent variable, will be the percent of a certain pollutant. And the dependent variable, or the y values, will be the cost in thousands of dollars to remove certain pollutant. And so we all know that global warming, it is real, and pollution, it is real too. So why don't we just clean the whole planet? Well, because it's very pricey. And in fact, this situation here, it shows us how pricey and how difficult it could be to remove 100% of certain pollutant. So you could see the points here on the graph. I'm going to write them down. So right here, to remove 80% of certain pollutant, it will cost not $55, but remember, $55,000. Two, if we follow this point right here, what it says is 90% of the same pollutant will cost 101,000. So it almost double, right? So now if we jump to 95%, that price, and this is in thousands of dollars, remember, that price is going to jump to $155,000. And that is according to this function right here. Now, if we were to set a goal to remove 100% of that pollutant, then the price will jump to $300,000. And that is just how weird these rational functions behave. They grow rapidly or they decrease rapidly. In fact, next chapter, which is exponential and logarithmic functions, we will cover some that they do the same. They decrease or they increase pretty fast, and they do actually have those asymptotes that we've been discussing with rationals. So now, just be aware that you could be asked questions like that on your homework where they present a graph to you and you have to analyze it. So for the next problem here, we have a summary of those horizontal asymptotes, but we've been covering that already. So we have that if you have a smaller degree on the numerator, that means that the degree on the denominator is bigger. And I like to refer to those as bottom heavy. So if you have a rational function that is bottom heavy, by default, the horizontal asymptote will be the line y equals 0, which we also know as the x-axis. The next case, well, that was case 1. Case 2, it will be whenever the numerator and denominator have the same degree. For example, here, degree n. And so in that case, we take the ratio of the leading coefficients. Right here, we're using the letters A and C just to generalize it. And that will be the horizontal asymptote. Now, the third case is going to be when the numerator has a larger degree. So we refer to those as top heavy. And so for those top heavy rational functions, there is no horizontal asymptote. They do have another type of asymptote, which is called slanted asymptote, but we're not going to cover those in this class. All right. One of the applications for these rational functions is what we call not only the cost-benefit function, such as the one we use here, but we also have this thing called the product exchange functions. And it gives relationships between quantities of two items that can be produced by the same machine or factory. That's the next example we're going to look into. For example, an oil refinery can produce gasoline, heating oil, or a combination of the two. An oil refinery, gas, heating oil, or a combination. The problem that we're going to cover is about a winery. So they produce wine, and they have red wine, white wine, or a combination of the two. And you know how this textbook loves word problems with alcohol. So we have the equation given to us here. And then, fun fact, based on the explanation of the equation, it says that we are going to use the variable x to represent the cases. And I'm not sure if this will be in cases. Yes, cases. The number of cases, not bottles, of red wine. And because these two types of wine are being produced at the same factory, then you could produce all red wine, or you can produce all white wine, or you could produce a combination of the two. So based on the problem, again, the white wine number of cases is going to be given by the letter or the variable y. So this will be the number, not bottles, but cases. Number of cases of white wine. So the question here for us is just to graph the function and find the maximum and the minimum quantity of each kind. Now, yes, this is a rational function. You could see that we have same degree. So we would have a horizontal asymptote if we use the concept of the ratio of the leading coefficients, it will be somewhere like negative 75 over 1, or just y equals negative 75. We also have this, the vertical asymptote, we can find it from there, and it will be something like x equals negative 1200. Now let's go back to what we mean by our variables. We're talking about cases of red wine and cases of white wine. So do we care about negative number of cases? No, we don't. Do we care about, well, yeah, that's all we care about. So for that reason, we are focusing our graph in the first quadrant, as you see it right here. So to find the maximum quantity that each kind of wine could be produced, we're going to be focusing on the x and the y intercept, because for the y-intercept, and it happens to be the point 0, 126. So what that tells me is that if we produce 0 cases of red wine, we could produce 126 cases of white wine. Now, according to the same formula, if we were to find the x-intercept, this will be the point 2000, 0. So what that means is that if you were to produce 0 cases of white wine, you could produce, the maximum will be 2000 cases of red wine. And that's it. That's the end of the problem. So now for the very last problem, we have here a retailer buys 2,500 specialty light bulbs from a distributor each year. In addition to the cost of each bulb, there is a fee for each order. So she wants to order as few times as possible. So consider like the shipping cost. In fact, Amazon is about to limit their shipping to just once per week per customer. So everything that you were to order, it will just be shipped to you once a week, and they're trying to cut their cost of shipping. However, the storage costs are higher. So now we have to consider two things: the shipping, but the storage cost. And those are higher than the shipping. So when there are fewer orders, hence more bulbs, light bulbs to store, then you're going to be increasing your storage cost. Past experience shows that the total annual cost for the bulbs, ordering fees, and storage cost is given by the rational function, and we have it here, where x is the number of bulbs ordered each time. So that is good to know. How many bulbs should be ordered each time in order to have the smallest possible cost? So in this case, we're looking for the minimum cost. And we have here our quantitative analysis that says that the x-coordinate will represent the number of bulbs at each time, and the y-coordinate is going to represent the annual cost of those many bulbs ordered each time. And so we have to go back to the problem and analyze certain things. First of all, the number of light bulbs that could order, which will be x, is going to be greater than or equal to 0, and it's going to be smaller than or equal to 2,500. And that is given to us here for sentence. Now, what we're going to do is graph our function in the calculator and make sure that you do enclose your numerator. So you, after the equal sign, so you go to your y equals, and then you will enter the numerator in parentheses. You must, because it is a trinomial. And then the division symbol, and then you could just enter x. Then you will graph your function, and you might not see the same thing that is here on the screen. So what you need to do is change your viewing window. So remember, you have to go to Window and change your settings so that your x minimum, your smallest x value showing on the screen, is going to be actually this one, 0. Then your x maximum that you want to see on your screen will be 2,500, because remember, that is the maximum number of light bulbs that they could order. Now for your y minimum, we're going to select negative 1,000 just to match our the screen here. However, talking about the smallest possible cost, so to me it would be actually better if we just make this a 0. Because in reality, we don't really, we don't care about what happens on the negative y values. Y is the cost. It's not like it's going to cost us $- to ship something. That would be like the post office paying us for shipping our stuff. That's never going to happen. So we could just set it at 0, cutting the window here. And then for the y maximum, here we're using 3,000. So you change your window, and then you will follow the following. You have to use the second key, well, if you're using a TI-84, second, and then find on the top row where it says calculate, calc. And then we want to find the minimum. Calculator might ask you, and if you see, our target point will be like somewhere here. So if they ask you for left bound, you want to position a point that is on the left side of your target point. Then this might switch to, and make sure you confirm with enter, so then right bound. So you want to select a point on the right side. Remember, this could also say lower bound and upper bound, same meaning. After that, you confirm with enter, enter, and then the calculator should give you this. Now, the minimum cost is this one, the y value. And the number of light bulbs, it will be here, 149.8299. If you are answering this question on the math lab, make sure you pay attention to how they want you to round. My guess is that they will say round to the nearest whole numbers, or in this case, it will be 150, because, I mean, you cannot ship 149.82 light bulbs unless one of those is broken, I guess. So this concludes the video for section 3.6. Make sure you do your homework, and thank you for watching.